Okay, everyone, welcome again to the next lesson. This lesson still falls under probabilistic modeling. Now we are looking at the queuing theory. Okay, this queuing theory is comprising of three different parts. It's a little bit extensive, so I categorize into three different parts so that you don't get lost in the middle. Okay, first we are looking at the introduction. Okay, what is actually a queuing theory? Okay, actually queuing theories fall synonymously with waiting lines. All right, if you are talking about any lines, that is a queuing theory. Okay, that makes sense, right? Okay, so what's the significance of this waiting line? All right, or a queuing theory? It comprises of three main important key players. All right, the first one, you have to know the arrival. Okay, arrival meaning whatever things, whatever people, or whatever product, for example, that comes in line. As long as you know how the arrival behave, then there is one particular key point. And then you have to know the actual waiting time itself, the behavior of the queue process. Okay, and then the next one is on the service facilities. Service facilities meaning that if let's say you have a system, whether your system have one counter, two counter, or is there a multi-phase or single phase channel? Okay, so we are going to look at this one more extensively later on. Okay, so what are these concept of queuing theory? Why is this important? Okay, why people talk a lot about queuing theory, and why, if you do some digging, okay, more digging later on, you can see that this theory is a well established theory among all the probabilistic modeling. Okay, it has on itself an extensive work on it. Okay, and there are lots of applications regarding this. Okay, why it is important? Besides, it is easy to understand, okay, and beside, it is easy to calculate and easier for you to especially when you start to look at the software, for example your QM for Windows or for your Excel. Okay, it is different compared to your previous models. Your previous model, you need to do a lot more work, okay, on the theoretical background. But queuing theory, okay, if once you know the theoretical background behind that, once you identify the distribution factors or distribution behavior that falls into arrival process or the queuing theory or all the background, okay, once you know that already, then the calculation is easy. Okay, you only need to, for example, if you have a single system, for example, you only need like what, two variables, not two variables, two quantity. All right, two independent quantity, you put inside the value, and then you click enter and then you get the final, all the information that you want. Okay, the average values and all the analysis available for you. Okay, so that's why people are so pumped with this queuing theory. Even though it is a very far back, okay, theory, it is still being used until today. All right, so the idea of really we dig that is besides of the easier way for you to solve that, okay, is because you are able to evaluate cost, and you are able to easily get the effectiveness of your service system. Okay, meaning that you can calculate, all right, whether you want to let's say you have a business, okay, for you to cater, okay, and if let's say you want to know whether your system is actually enough, you can you can create your system based on your available counter, for example, or whether you can hire another staff, and then you can reduce a lot of your waiting time, and you can improve on the efficiency, but at the same time you are able to cut cost. Who wouldn't like that, isn't it? Okay, but is the introduction of extra stuff necessary for you to make your system efficient? Okay, that is the question. Sometimes we think that by producing better services, okay, or producing a lot more counter, for example, introducing a lot more counters, sometimes it does not efficient. Okay, why? Because there are certain counters, for example, you can reduce the waiting time, but you cannot. You can the satisfaction is, does not increase significantly, but it increase your cost significantly. Don't you see that? Okay, it reduce a little bit of the waiting time, but at the same time, your increase of costs does not give way. The trade-off is not that, it does not make sense. All right, so that is something. Okay, that's why we need to see how we are able to get this, we call that a trade-off, okay, between sensible waiting time, all right, and at the same time increase our efficiency, and we get the matching point between these two important variables, okay, that we need to consider. Okay, so this is, as I mentioned earlier, ideally, okay, what level of service should we provide? Okay, we want people to really satisfy with our service, but but at the same time we couldn't get the expense of the thing that we want to provide. All right, so if we can also control this level of service, can we actually find the balance? Okay, so the balance in the previous example, as I mentioned earlier, your trade off. Okay, whether can you find the balance to? Can you find the service versus cost of the waiting time? Okay, so if you are able to make full use of this advantage of this knowledge, okay, then you can be able to heighten or increase the efficiency in whatever things that you do. All right, so that is the most important thing, right? Okay, so to recap, you need to get your service level the max as you can, and you need to reduce your waiting time the least that you can. All right, so the questions involve, for example, counters, staff, facilities. Okay, these are some of the question. Okay, so how can we able to actually put that in action? Okay, are we going to do a try and error approach? Okay, try and error meaning that today we are going to open two counter and see and observe what happens. Tomorrow we are going to do another open, like another five counters, and see what happens. So is there a good way to do that? All right, it must not be so, isn't it? All right, that is why we start to try to look at the queuing theory or queuing process, meaning that you do the modeling. Okay, how you do the modeling? As we always we recap back from our previous lessons. Okay, if let's say you have a system, okay, in this case a problem, for example, in this case a problem where you are dealing with a line, okay, or you are dealing with a queue process. All right, so you need to first make a very extensive observation first. Okay, but in this case, your observation is not coming from a try and error for like infinitely many time. Okay, because you have a constraint of your cost or your days. For example, it is not efficient and it's not effective. Okay, so normally you do some observation in quite extensive period of time, and if that's enough, you transform or translate all your observation inside your modeling queuing system. Okay, and by the end of the day, you do some simulation. If let's say you are able to do the simulation, you do some simulation and see which fits with your current available observation that you have. Okay, and then if let's say this kind of simulation can give you advice on, for example, opening two counter instead of three, or if let's say you are able to heighten a little bit on your service efficiency, your cost you heighten a little bit, but at the same time your waiting time can increase a little bit more compared to the previous. If let's say you reduce your counter, then you make the best decisions. All right, so that is the concept. Okay, so this I give you for the most important, the most important cue, for example, especially in a logistic issue. Okay, there are lots more other application. Okay, we are going to look at it later. All right, but the most significant one is on the logistic application. All right, logistic means, for example, if you are very keen about Air Asia, okay, why Air Asia not MAS, for example? Okay, because you know that Air Asia is the low cost. Okay, it pride itself with a low cost airline. All right, so low cost airline meaning that you cannot you cannot you cannot trade away, okay, with your inefficient business cycle. All right, you cannot do that. All right, you cannot trade off your quality on especially on the time. Okay, you need to make sure that whatever system that you are in, okay, whether the cargo handling, whether you the way you do your luggage handling, or the way even you handle your a human, okay, because you are a human carrier, for example, a human carrier and also a cargo carrier. Okay, so the way you handle all these things, it must be efficient. Why it is efficient? Because it is a low cost airline. Okay, low cost airline meaning that you cannot afford all the unnecessary items. All right, that's why, for example, you have to make sure in an Air Asia, for example, if you notice the time on the ground, it has certain control, okay, certain quality control. I cannot remember how many minutes that one particular aircraft, okay, must be on the ground in less than how many minutes. Okay, they have a quality control for that particular minutes. Okay, why? Because they believe that once they have the airline, okay, once they are having an aircraft, meaning that all their aircraft produce money when they are on the air, in the air. Okay, why? Because that's the function, isn't it? Okay, it's a function of an aircraft. Your function of an aircraft is not on the ground. Okay, so meaning that if you are on the ground, okay, if your aircraft is on the ground, meaning that your aircraft is not productive. Okay, that's why they are very, very critically serious, okay, on making sure that their time in on the ground is so much less compared to their counterpart. Okay, counterpart meaning that a more lucrative business. All right, a more like Malaysia Airlines, Singapore Airlines, for example, because they don't have that needs to make sure that uh, they function in a very efficient manner. Okay, but this particular low cost airline, they have to do that. Okay, that's why they have to make sure that their queuing process, the way for example, if you are a passenger, the moment you start checking in the line, okay, you notice that it is very different than when you do an exclusive when you go to an exclusive airlines, right? Okay, it's because the moment you go into the system, you notice that the whole time you go to the system, it is calculated in a timely, it is calculated in a manner system. All right, so I hope that makes sense. All right, okay. Okay, so the by the end of the day, what we need to find is actually the total expected cost. Okay, so the total expected cost is coming from the sum of your service cost and also the sum of your waiting cost. You have the service cost more or less in the sense of your service. You provide your service level earlier, and then your waiting cost is what happen if, let's say, you cannot make the process, for example, go out from one entry to the next entry as fast as you can. So that is your waiting cost. Okay, your service cost is on the service facilities, and your waiting cost is what happen if, let's say, you look at the airline just now. Okay, aircraft. What happened when your aircraft is not being attended on the ground? Okay, so that is the cost. You put them together, you need to find the total expected cost for these two sum, all right, of these two costs. Okay, so once we get the total expected cost as expected, we need to get the minimum value for this total expected cost. All right. So once we get the minimum value, that is the most efficient system that we have and that we need to adopt. Okay, so that makes sense, right? Okay, if let's say these are the graphical illustration to understand that, but you have to understand, okay, all these graphical illustration, it comes from the next modeling, okay, behind that, okay, on the background. For example, you have a model for your cost for service, and you have a model for your cost of your waiting time, and you can expect your total expected cost should be something like a curve like that, and then the cost benefit analysis in a way like this. All right, so the matching point between these two should become your minimal total expected cost, which should become your optimal service level there. All right, so that is the concept. Okay, now let's move on to one example, because I think you need to know a little bit how this thing happened. All right, so let me remind you, this is just a simple example for you to at least get the concept of total cost. That one, the total cost. Okay, not on the queuing model. All right, the queuing model we will touch on it later on. This example is a very straightforward. There is no such thing as the arrival time depending on what type of distribution. All right, it is just based from observation process only. Okay, so think of it that way. Okay, this idea is just for you to understand what is the cost waiting time and what is the cost of the service and what is the total cost between these two. Okay, so let's start with the example. All right, you have this shipping company. Okay, you have a docking facility in the river, and then on average, there are five ships that will arrive and unload their cargo. Okay. And then five ship per shift. Okay, per shift. Meaning that now we are talking about whatever happen if we rearrange or if we play around with the shift in this case. All right. So the average ship stay as it is, five. Okay, and we know that idle ships are expensive. Okay, as I mentioned in the aircraft example earlier. And then we know, makes sense, right? If you want to hire more staff, okay, that makes sense because you can reduce a lot more on the waiting time for the ships. Okay, for you to process the ship. Okay, but then it also expensive. Okay, right? So this company try to determine the optimal number of team per shift. All right, so that they are able to get the minimum total expected cost. Okay, so what happened next? All right, so these are the scenario. Okay, you notice at the upper part of the number of team of workers that work on that particular shift. Let's say we have shift one shift sorry on the let's say we have on the shift the one at the top, one two three four, representing if, let's say, one worker works in the shift. Okay, if let's say you have two, meaning that there are two workers work in that particular shift. Yeah, if let's say you have three, meaning that there are three workers work in that particular shift, and the same thing for four. Okay, and for A, average is still the same. Okay, we expect that on average we have five ships comes together and dock at one particular shift time. Okay, so five. Okay, now you notice this one is coming from the observation. Okay, if let's say you have the B over here, right? These are the average time each ship will need to wait to be unloaded. Okay, in an hour term. For example, if let's say you have one worker per shift, your waiting time, all right, is 7 hours. But if let's say you introduce two workers per shift, your average time, waiting time now becomes only four. Okay, it reduces a lot, right? 7 hours to 4 hours makes sense, isn't it? Okay, this one is just an observation. All right, so if let's say you have three workers, okay, so you can see now the three workers, your average time now becomes three. And of course, if let's say this one is the most efficient one, okay, if let's say you have four workers, of course your average now reduced from one worker seven until four workers, you have two only, 2 hours only that your ship need to be docked and do nothing. All right, okay, so based from these problems, do we need to get four workers? Okay, but you have to remember four workers, meaning that you have to give four times the salary, okay, from the previous worker. Okay, that is not that cheap, right? Because once you have a business, you have to make sure that the salary is like an obligation for you to fulfill. Okay, no matter you have business, on average you have five. Okay, five. Even if on average you have the ship that comes, let's say today the ship comes one only, you still need to pay for four workers. Okay, when we put that in perspective, okay, it's no longer easy decision, isn't it? Okay, so we proceed to see. Now we have the average number of ships that arrive, and we also have the average time that ship need to wait to be unloaded. Okay, so C is the time, the total ship hours lost per shift. Okay, meaning that it arrived but nothing happened. Okay, so if let's say you need to find that total hour, it makes sense, right? You just multiply your A and B. Okay, that's why you can see over here 35, 20, 15, and 10 coming from the multiplication of items A and also items B. Okay, that one is clear. A, B, C. That one is clear. Now, we proceed now to the cost of our workers. Okay, that is that expensive. Okay, so in this case you are talking about the service time, sorry, service line here. Okay, the service line there. Okay, so if let's see, all right, you have the sorry, we need to get the estimated cost per hour of idle ship time first. Okay, if let's say this one is constant, okay, in the case, you estimate that 1 hour idle ship time, it costs you $1,000. All right, so once you have D, okay, you can get the value of the ship lost time, isn't it? Makes sense, right? The ship lost time should, you can just simply multiply your total ship hours, which makes sense. You multiply with the cost per hour of idle ship time. Right, because okay, if let's say the time lost is 7 hours, and then on average it's the ship arriving per shift is five. Okay, so your total ship loss shift per hour is 35, and then the value of the overall ship lost time should becomes that total ship hours you multiply with the per hour estimate. All right, so that's why you have 35,000 there. Okay, so similarly, you put the same thing there. Okay, 35,000, 20,000, 50,000, and 10,000. Okay, now we look at the salary, all right, the service cost. Okay, so you can see over here, if let's say my salary, okay, for one particular stuff, okay, I'm talking about this stuff is more or less the same. Okay, the experience is the same. So one staff we give them 6,000. All right. So if let's say two staff, you can just multiply 6,000 by two, isn't it? So you get 12,000, 18,000, and 24,000. Okay. So as we mentioned earlier, our total expected cost is the total cost for your waiting time and also the total cost for your service, isn't it? Okay, so your total cost for your waiting time is 37 for staff number one, for example, 35,000, and then your total cost for your service, all right, service meaning that your salary in this case is 6,000, so it becomes 41,000. That is the total cost that you need to expect if you have one staff in the dock, okay, to unload the ship. Okay, so if you are able to calculate for one staff, okay, then you do the same thing for your two staff, three staff, or four staff. And then surprisingly, okay, you notice if you put if you consider two staff, your total expected cost is 32,000. But if you put three staff, see, even though your estimated cost per hour either reduce a lot, okay, in that case, your value of ship lost time instead of 35,000 now becomes 15,000, right? But then you cannot forget the service level. Okay, your service level in this case representing F now becomes 18,000. Okay, even though it lost the ship lost time 15,000 only, but then your salary increased a lot, which is 18,000. And when you total them together, you have like 33,000. Okay, and then the same thing happens for your valuation for four staffs. Now you have 34,000. Okay, so in this case, okay, you can find the minimum total expected cost among all your alternatives. All right. So in this case, you need to find the minimal cost. All right. The minimal cost, which means in this case is 32,000. All right. So this is your optimal cost right now. Okay, so you notice this one, as I said earlier, this is just the example, the simplest example possible, okay, for you to understand the concept of total expected cost, all right? But as I mentioned earlier, once we have the system or once we have the machine, you can always put this into your automation, all right, so you can automate this calculation, so you can do the simulation. Whatever happen if your average now is not 5 anymore? Okay, whatever happen if let's say you want to see how many teams, how many number of teams that you need actually in this particular issue? You cannot do it try and error, right? You cannot just simply today you um, employ two people, tomorrow you employ another two people, so you get four staffs in you, and then the next day you think, oh, try and error, this does not make sense, and then you cut your staff into two. You cannot do that, all right, because once people get into the system, the way you want to retrench or the way you want to retrench, okay, then it is not as simple as kicking them out of the door. Okay, there are lots of the things that you need to consider as well. Okay, so that's how the main idea of how we get the total expected cost. Mm. Okay, so that is the introduction. So now I'm going to show to you, okay, the more complicated matters, okay, more make sense of the day-to-day problem or application or what type of queuing theory or waiting time that we need to consider, because you don't have one particular problems with one particular solutions only. Okay, that is the problem with the queuing theory. Okay, but what you need to see as I already mentioned earlier, you need to always remember these three things. You need to know the arrival process. You need to know the actual waiting line process, which is the queuing itself. And then you also need to know the service facilities, which is the channels or the phase, all right, or something similar to that. Once you understand exactly these three characteristics, then you are able now to develop your mathematical model. Okay, the most important part is actually to identify the characteristic behind these three different parts. Okay, so as usual in modeling, this identification, that one is a little bit tricky, and that's one is something that needs more reflection, and you need to look at different observation. For example, whether you do it on your own, or you can always look at the historical issues or how people see things based on their particular problem, and you can adopt because normally the behavior is quite similar among each other, right? For example, if let's say you expect people to arrive and go out from the system, arrive, go out from the system, it's quite similar actually. The difference is on the little bit of the behavior of the time span or something like that. So you can adopt that particular behavior in line with the previous examples. And then only you can develop your own mathematical problems into your own application or into your own practical problems, right? Okay, so we first look at the arrival characteristic. Okay, so what you need to really understand is the size. Okay, the size of the calling population. All right. So the size meaning that you need to know whether you are talking about your arrival size, whether it is a finite value or infinite. Uh, for example, in a bank, okay, your bank cannot be infinite number, right? Because by the end of the day, the bank will close its door at 4:30. Okay, so that is finite. But let's say if you are talking about a system, for example, your unified data. Okay, for example, if you go inside the website is also a channel. Okay, like for example, a host or a Google. There is no finite at all. Okay, because every time there are lots of different data coming and going. So that is infinite. So it's unlimited, is limited, so it depends on your problems. And then you need to know the patterns of arrival. Okay, patterns of arrival meaning that is there any particular pattern that follows certain distribution? All right. For example, normally people will create random arrival will follow the Poisson distribution. Okay, if you forgot about Poisson distribution, you can come back to the statistical distributions. Okay, and but if let's say you know, okay, by right, this particular arrival follows certain we call certain exact situation. For example, in 10 10 minutes, one people come. 10 minutes, one people come. Okay, I'm not sure what type of system we are talking about. But if let's say you have this particular behavior, then your random pattern must follow that particular exact distribution. All right, so it depends on your problem. Okay, and then this one is a little bit idealistic. Okay, but whatever it is, as we know, mathematical model, we need to have some assumption. Okay, because there's no perfect system whatsoever, right? We can only improve over time. All right. So the most idealistic assumption in the queuing system is this. Okay, the first one. Most queuing model assume customer are patient and will wait in the queue until they are served and do not switch lines. All right. So this means that we ignore, for example, we ignore the concept of bulking, meaning that I don't want to join the queue if I see a lot of people in the queue, which is in a which is in a practical form. I think, for example, if me, I go to some place to get the service and I see lots of long queue, I will go another day, right? And then, for example, if let's say I'm already into the queue and I get upset, okay, because the service is lousy, I will leave without receiving my service. That one is practical. That one is common, isn't it? But unfortunately, all this behavior, okay, we didn't take into account in this particular queuing system, at least in our discussion. All right. But if let's say you want to improve on the system, okay, which is a little bit difficult, I'm not sure doable or not, but if let's say you find ways to incorporate these particular issues, then that will be fine. Okay, your valuation of the mathematical modeling will be a little bit different. Okay, and you can improve so much on the theoretical development of this model. Okay, so now we talk about waiting line. Earlier we have arrival characteristic. Now we move forward to waiting line characteristic. Okay. The same thing happens here. Okay, you also need to consider the line itself, whether it is limited or unlimited. Okay, this one is important. Okay, so right now in our case, we normally focus on the first in, first out situation. Okay, why? Why? Because we talk about receiving service, for example. Okay, because if you are looking at another rule, okay, if let's say you're not familiar with this rule, there are other rule which is so complementing this first in first out rule. We call that last in first out. Okay, last in first out, meaning that if let's say you have a store, you put the first in last out, for example. Sorry, last in first out. Okay, for example, if you put the big, okay, the heavy product, okay, let's say you put a bat, okay, very heavy, right? And then you put on the at the at the very deep end of your 2 by 2 2 by 2 in your unit cubicle, for example. Okay, it does not make sense, right? If you want to take out, you need to make sure that everything out there move out first, and then you take only that particular, the heavy product that you have at the deep of your cubicle. And then once you get that, you put back all the you put back all the product inside again. It does not make sense, isn't it? Okay, because it's heavy, and then it give you a lot more heavy lifting to do it. All right, but by the end of the day, you know that this particular product does not have any due date, for example. Okay, it's not perishable. Okay, it's not like a vegetable. You cannot consume this into just one week, for example. You cannot. Okay, you don't have to. Okay, it's better if let's say we don't have any expiry date, it's better if you take out the first one that you can reach, isn't it? So the first one that you can reach inside that main cubicle of your storage is actually the last one in. All right. So that is what it means by last in, first out. Okay. So that is another story, right? Okay. But in this queuing system, okay, we mostly normally focus on the common rules of first in, first out. Okay. The idea is that if you are doing your grocery, you queue in a counter to check out your items. Okay. By right, if you are on the first line, you will be serviced first. Okay, the second will go second, the third will go second. Okay, that makes sense, isn't it? Okay, we forget the idea of people coming and cutting lines. Okay, that one is another story. Okay, but in idealistic queuing system, this is what we need to consider. All right. Okay. Now the service facility. The service facility is interesting. It's not that another two is not interesting, but the service facility, meaning that there are different elements that you need to consider once you identify your service facility characteristic. Meaning that once you know the number of channels, the number of service, the phase of your channels, okay, then you can tie with different model that reflect with these particular channels office, and then you can solve that as it is. All right, I'll show you later. Okay, so these are for basic. Okay, basic, meaning that there are a lot more, but these are the most common. Okay, queuing system configuration. The first one, the simple one, the simplest version, you have one channel, one phase. Okay, meaning that your arrival from your left hand side and then your output departure after service. That's it. Okay, that one is the first one. And then the second one, you have one channel, but you have multi-phase system. Okay, multi-phase system meaning that your service, you need to get your service not only one time. Okay, that's why you have type 1 service facility. You go out the system and then you need to go through another type 2 service facility, and then now you go out from the system, departure after service. Okay, it's not just only one particular phase. Okay, that one. And then you have multi-channel, but you have single phase system. Multi-channel single phase system meaning that, okay, you have uh if you want to put that into a channel too, is into a counter. Okay, now you have three different counter, for example. Okay, not limited to three. Okay, so you have one single line, but you are now able to move away from only one particular counter. Okay, in this case, you have three different counter, but then after that, you can go departure, departure, departure. Okay, so by right, it can reduce waiting time quite significantly depending on your uh, channel, right? Okay, the next one, you have multi-channel, you have multi-phase. Okay, so for example, you are in a queue and then you go to either type 1 or type 2 counter, and then after that you go to either type 1, either service facility 1 or service facility 2, and then only you departure. Okay, there are also like uh, s- uh, multi-channel, single phase, okay, and something like that. Okay, but this one is basic, the four most basic configuration. There are lots more depending on your situation, but by the end of the day, rule of thumb, this is the most common. These are the examples. Okay, if let's say you have just one single channel, you can look at it in a one checkout counter in your grocery stores, for example. Okay, a small grocery store with only one checkout counter. Or if let's say, for example, like right now, we are dealing with a pandemic. Okay, normally when you go to the service counter, a small supermarket in your nearby your house, okay, you can see they only open one single channel because by right no one wants to go out right now, isn't it? Okay, so it does not make sense to open two or three channels just for the sake of handling small shopper. Okay, so for example of multi-channel, okay, if let's say you have a call center, okay, you call and then you are being, for example, like, okay, if let's say you have good, if let's say you have good uh, uh, experience with the call center, the chat center provided by AirAsia, for example, okay, you need to wait, okay. If let's say you are able to being channeled into a people oriented chat room, okay, I'm not talking about the Eva um, virtual customer service, okay. If let's say you are able to being diverted, okay, into customer service, all right. So you can see in the platform there in Asia channel, you can see, okay, you are on the 500 50, the your queue is 50, okay, you need to wait about approximately blah 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 hours, so meaning that you are inside the system already, you are in the 50 on the 50 queue, but you cannot expect they only have one rep, right? Okay. So once you are already in the position one in the queue, and then you are diverted into either one of the channels. Okay, either one of the channels of their customer service, right? So that is what we call a multi-channel. Okay, and then single phase. Okay, single phase, for example, like multi-lane tool booth road. Okay, there are lots of booth roads. Okay, but whatever, even though it has lots of toll booth, but the phase is only one. Okay, meaning that you only need to touch in or touch out, doesn't matter, but then that's it. Okay. But if let's say you have a multi-phase, for example, like an automatic car wash or a drive-through, meaning that you have different phase that you need to work on, that you need to go through. For example, if you go to an automatic car wash, first step you need to put your car into a bubble, la 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 bubble, and then you move out from that bubble, okay, and the and the car drive on its own, and then they go into another phase, okay, which is your car needs to be wiped clean, all right, and then later your car needs to be vacuum, okay, so that is the meaning of multi-phase issues, okay. It does not meaning that you go to one particular phase and you get the service, you go out from the system. No, this one you need to go through few other different system. The same goes through the drive-through fast food restaurant. Okay, once you need to before you can pick up your food, okay, you need to go through the first level, okay, the and then you need to make the payment. All right, you need to order payment and then only you get the food. So that is the concept of service facilities. All right. So that's the meaning of it. And that's why this particular service is very important because it can reflect most of the information inside your model that you need to consider later on. Okay. Okay, so this one is just the distribution. Okay, similarly, okay, we are going to look at this particular distribution. For example, in part two, I think would be easier for you to know and see. Hmm. Actually, part two and part three. Okay, all right. So this is the thing that I want to highlight. Okay, because this one you will need to always see this in part two and part three, and also during your experience with queuing theory, you see a lot of this. Okay, we call this a candle notation. Okay, the candle notation, what you need to really know is M, D, and also G. All right, and then this M, D, and also G, you put inside your three main characteristic that I mentioned earlier, your arrival, your service, and also your channel. Okay, so your arrival, your service time, your channel. Okay, so how to move about this? Okay, I'll just give you example like this. Okay, if let's say you have MM1 like this, it means that uh, it means that one referring to single channel, the first M representing your arrival, okay, with a Poisson distribution, okay, a random distribution, and then your service time is also a random, okay, exponential service time. Okay, so you have the first arrival, okay, I show you earlier just now. Your first arrival is M, your service time is M, your number of service channel open is 1. The same thing happen if your channel now becomes 2, okay, your candle notation now becomes MM2. And if if you look at this third model, okay, you have MD3. Okay, what's the difference? Okay, 3 is straight away, you have 3 channels. Your arrival is Poisson M. Okay, just a Markovian. Markovian is actually just just a random actually. Okay, but now your service time is constant, meaning that if let's say your counter by hook or by crook, your counter only able to give you 5 minutes, only 5 minutes. That's it. No less, no more, which is so surprisingly good, right? But okay, maybe you feel like, there is no such thing as that. Okay, there is no such thing as that when you think about service time in the sense of human. Okay, but if you look at this particular queuing system in a manner of production line, for example, okay, that makes sense, isn't it? For example, if you produce a car, okay, and then you have a multi-phase of your car, all right, and then for example, your car, they put the most important part in the car. For example, they install the door. Okay, they install four doors. You can expect, right? If they install four doors together, it is a machine doing the job, right? And if the machine doing the job, unless there is no breakage or problem with the automation or whatever, it has to make sense. If you are dealing with machine, your time must be perfect, isn't it? For example, if let's say your machine are able to install four different doors in 5 minutes, so all the time, the machine should produce 5 minutes time to install four doors in one car. See? Now you can see, oh yeah, we have a constant service time there. Okay, so for this kind of example, you have this MD3. All right, and so the same thing happens. You can see over here, the second one, MG4. Okay, so you may feel like, what is G? Okay, you can go back to this. G is whatever distribution, but you need to know the mean and also the variance. Okay, meaning that your distribution is not just on the Markovian behavior. Okay, because there are lots more distribution out there, isn't it? You have an like what uniform distribution and a lot more. Okay, with itself different kind of uh, statistics behavior. Okay, so I think that's about it. Okay, for part one. Later part two, I'm going to show you the easiest system. The easiest system, and then together with the automation. But since you already know the automation using QM for Windows on the previous simulation technique, and also from the previous even deterministic modeling, so I'm going to go fast. I'm going to just show you the output only. Okay, not on the DIY how to. Okay, if you are not able to do that, you can go back to the previous video. Okay, so I hope you will look forward for the next lesson. So I'll see you guys soon. All the best.